Okay. Okay. Hello, sir. This is Kirtana from Mechanical Engineering. I'm doing the project called Emotional Classification with BERT model. Actually, building a deep learning model on the MELD dataset. So, about the introduction, this presentation outlines a project focused on developing a deep learning model for emotion classification using the MELD dataset, employing the BERT transform model for texture analysis. So, the objective of this project is building the text-based emotion classifier. So yeah, initially I tried to focus on speech and text parallelly, but as the time constraint is here, so I worked on the text-based emotion classifier. So the main goal is to develop a classifier that accurately detects emotions present in dialogue utterances derived from the MELD dataset. This involves using BERT to analyze and interpret these texts, providing insights into various emotional expressions. So, this is the exploratory data analysis I got from the files. There are three files. The first one is a devsenmo.csv. Second file is test underscore send underscore mo dot csv, and the third file is main underscore send underscore mo dot csv. So while doing the exploratory data analysis for the first file, as you can see this graph, it is a distribution plot. Here we can see the emotional label imbalance, especially the dominance of neutral joy, should be addressed during training. तो class weighting, sampling, or loss adjustment. Utterances are diverse and speaker distribution is skewed. Some characters are dominant. Some characters are dominant. Here we can see. The time-based and meta columns like episode, start time can be dropped unless used for advanced modeling. So it is useful for understanding the context depth available in dialogue threads like dialogue ID, utterance ID. So in this uh, in this distribution plot, we can analyze this only. And while we can see this correlation matrix, we can see that we can see that in the serial number and the dialogue ID, where we are getting a correlation result of 0.96. Here we can see that. It is a very strong positive correlation. The serial number, the index actually progresses almost linearly with the dialogue ID. This suggests data is sequentially ordered by dialogues. And serial number and episode, here we can see serial number and episode. Yeah, here we can see. Yeah. Here we can see that moderate positive correlation. Serial number slightly increases with the episode number, again confirming chronological order. Dialogue ID and episode. We can see the dialogue ID and episode here, which is where we are getting 0.35. Somewhat correlated, higher dialogue IDs tend to be from later episodes. Utterance ID and episode. Here we can see that utterance ID and episode here. Here we can see a result of minus 0.27, which is a weak negative correlation. Utterance IDs tend to slightly decrease with the higher episodes, possibly due to shorter dialogues or few turns in later episodes. Utterance ID and dialogue ID, we can see here, where we are getting minus 0.07, which is like negligible or weak correlation. Utterance index with a dialogue is not related to dialogue ID, which makes sense. And season and others. So while considering season and others, we are getting a close to zero. Close to zero, because here it is showing very weak or no correlation. Seasons are almost uncorrelated with the serial number, dialogue, or episode. This could be due to interleaved or uneven distribution of scenes across scenes in the subset. So high correlation between serial number. So high correlation between serial number and dialogue ID indicates that data rows are mostly ordered by dialogue progression. So season and episode are not strongly correlated with the most other variables, so you can treat them as independent categorical or meta features. Utterance ID is relatively independent, which is good. Modeling each utterance without strong bias from ordering is possible. There are no redundant features with a perfect correlation other than serial number versus dialogue ID, so dimensionality reduction is optional. So yeah. So while going to the second file, you can see in the distribution graph that a clear overview of the dataset structure and class representation. The utterances are spread across a handful of speakers, with Joey, Chandler, and Rose being the most frequent, indicating that these characters dominate the dialogue in this test split. Emotion labels are heavily skewed towards neutral, followed by joy and anger, and while categories like disgust and fear are underrepresented, suggesting a notable class imbalance. Similarly, neutral sentiment is the most common, with fewer instances of positive and negative sentiments. Most dialogues come from season 4 and 5, particularly concentrated in specific episodes, which could affect the generalizability of models trained on this subset. The utterance and dialogue ideas show that dialogues are short, often with just a few exchanges. Overall, the test set maintains a realistic conversational structure but exhibits a clear imbalance in emotional and sentiment labels that needs to be considered during model evaluation. So while seeing the correlation metrics, serial number and dialogue ID are strongly positively correlated, where we are getting 0.97, which makes sense as dialogue ID is likely increased sequentially with the raw numbers. So utterance ID has very low or near zero correlation with the most other variables, suggesting that the number of utterances per dialogue varies and is not tied to order, season, or episode. Season and episode show a strong negative correlation minus 0.78. Here we can see that indicating that higher season tend to contain lower episode numbers in this subset or vice versa. This could be due to selective episode sampling in the test set. Serial number or dialogue ID and season show moderate positive correlations nearly 0.32 to 0.34, meaning rows and dialogues are somewhat aligned with the season progression. Episode is negatively correlated with the several features, including serial number, dialogue ID, and season, highlighting some inverse structuring in how the data is distributed. So in the third file, trains.mo.csv, you can see that serial number shows an even spread, suggesting uniform sampling across the dataset. Utterance, that is test values, are all unique for nearly unique, indicating by the flat low height histogram. Here we can see that. Low height histogram. These are specific spoken lines from the dialogues. Speaker distribution reveals that a few characters dominate the dialogue, such as Chandler and the woman, while others like Ross and Phoebe appear less frequently. Emotion is clearly imbalanced, with neutral being the most common emotion by a large margin, followed by happy, while emotions like sad, disgust, and anger are rare. Sentiment shows a skew toward neutral, followed by positive and relatively fewer negative samples. Dialogue ID distribution suggests several short dialogues, with a few occurring more frequently. Utterance study indicates that most dialogues consist of a small number of utterances, 1 to 5, with a few reaching higher counts. Season and episode are unevenly distributed. Some seasons, example season 5, and episodes dominate, indicating possible data collection bias or focus on select episodes. Start time shows all values are unique or nearly so, reinforcing that each utterance is from a distinct time point in an episode. So while going to the correlation matrix, you can say strong positive correlations in serial number and dialogue ID, where you are getting 0.98. These two fields are highly correlated, suggesting that dialogue IDs increase almost linearly with the serial number, possibly due to the dataset being ordered by dialogues. Season and episode 0.95 we are getting. There's a very strong correlation between the season and episode columns, indicating that episodes are sequentially distributed within seasons and perhaps across the dataset. Serial number and dialogue ID are also strongly negatively correlated with the season and episode, around minus 0.833 and minus 0.68 respectively, implying that lower dialogue IDs occur in later seasons, episodes, or vice versa. Weak or no correlation. it's happening in adherence side. It shows very low correlation with all other fields, implying that the number of utterances per dialogue. Okay, sorry. The implying that the number of utterances per dialogue varies independently and doesn't follow a strong trend across the other features. So negative correlations, serial number and season, where we are getting minus 0.83, and dialogue ID and the season, where we are getting minus 0.84. This could suggest that the data may be ordered such that earlier dialogue IDs and serial numbers are associated with the later seasons, possibly due to sorting strategy using during dataset creation. In summary, this matrix helps reveal structure in the data, such as ordering and grouping logic. For modeling, it shows the utterance ID is independent, while other columns like season and episode and dialogue ID are interrelated, useful for feature selection or understanding redundancy. So, fine-tune BERT on MELD labels. This project aims to fine-tune the BERT model to classify emotions from multi-party conversations within the dataset. This process includes optimizing the model's parameters based on labeled data corresponding to different emotions such as joy, sadness, anger, and more. So, analyzing the training dynamics, it monitors the model's performance metrics across training epochs. It includes observing training loss and validation accuracy to ensure the model converges properly. Any fluctuations or instabilities in validation performance can indicate issues such as overfitting or the need for hyperparameter adjustments. The workflow is the data loading and the pre-processing. It contains multiple CSV files representing training, validation, test sets, splits. Key processing steps include removing rows with missing labels and encoding the emotion labels into a numerical format. Using label encoder, ensuring the data is ready for modeling. So the model architecture and training loop, it is built using word for sequence classification with a classification head above the CLS token embedding. The training loop integrates custom functions for training and evaluation, employing the AtomW optimizer for effective learning rate management while tracking performance throughout the training process. So we can see here the evaluation metrics. Like here we used many metrics like precision, recall, and effort score for each emotion category. So it is essential for understanding model performance and generalization capabilities. Here we can see the graphs of training loss over epochs and validation accuracy over epochs. So in the training loss of epochs, the training loss starts at around 1.2 and rapidly decreases within the first 10 to 20 epochs. Then gradually levels off and stabilizes near 0.08. It indicates that model is learning from the training data effectively and it minimizing the error over time. The flattening curve shows that further training doesn't significantly reduce loss after a certain point. The validation accuracy over epochs, the validation accuracy starts at around 0.62 but fluctuates heavily throughout the training process and gradually decreases ending near 0.57. This suggests a classic case of overfitting. While the model performs better on training data as seen in the loss, its performance on unseen validation data worsens over time. This model is likely memorizing the training data instead of generalizing well. So the training is effective for the training set as indicated by a consistent loss reduction, sorry. Generalization is poor as shown by the decline in validation accuracy. This implies the model may need regularization, example dropout L2, early stopping more training data or better architecture. So in conclusion, in summary, the process of building an emotion classifier using BERT on the MELD dataset involves meticulous steps from data pre-processing to model evaluation. By continuously analyzing training dynamics and performance metrics, the model can be fine-tuned for optimal accuracy in emotion detection. So thank you. Um, yeah. So this is my GitHub repo where I uploaded all these things. As suggested in the document, as suggested in the PDF, like I uploaded my motivation, how does it connect with the past, current, and current work done in multimodal learning, like in the with the perspective of historical, and learning from this network, the learning from this work, and the analysis of the graphs I got. You can see that here. And what surprised me in this project, and what can be the scope for the improvement. I include the references I mainly looked into. Actually, it is the dataset reference, and it is the paper I looked into. So it is the GitHub repo. I uploaded everything. So yeah, thank you.